Okay, in this podcast, we're going to take a look at the kinds of things that we do in the lab. So let's go ahead and get started. So first of all, if I'm looking at the scientific method, um, we have a nice, neat presentation here of the scientific method, but in fact, it's not always quite so simply done. But generally, I start with some observation or some question about something. I develop a hypothesis based on doing some research. It's an educated guess, so it's not just, pick something out of thin air, but I do some research on what other people have done or what people have said about this observation or this question. I develop this educated, based on research, hypothesis, conduct an experiment to see whether or not the hypothesis holds, and based on the results that I analyze, I develop some conclusion. Now, I might have some conclusion that doesn't support the hypothesis, and I might need to go back and restart. I have some observations that came out of this that says I need to change my question or revise my hypothesis. So let's talk about the types of variables. So we have control, manipulated, and responding variables. So the control are the variables we hold constants, and sometimes we call these constants, okay? And then we have the manipulated variable, which is sometimes called the independent variable, and this is the thing that we purposefully change. And then the responding variable is the data that we record, the things that we're measuring as a result of whatever we change in the manipulated variable. And the responding variable is often called the dependent variable, okay? Because its result depends on the independent variable. Okay, in experiments we generate numerical results, which we also call quantitative results as opposed to qualitative. Quantitative result means there's a number in it, okay? In the lab we measure things like mass and volume and pressure and temperature, a lot of stuff, right? There are two types of errors that we can measure that we have in our measurement. There's systematic and there's random. So the systematic is a function of the measuring device, and the random is related to the laboratory technique. So systematic, let's think about that. So if I am measuring, let's say, the volume of water in different glassware, if I am using a beaker, I am going to have more error than I will if I use a graduated cylinder, because the graduated cylinder has finer graduation lines. It is also made more precisely, so I'm going to have less error in better glassware. Okay, so let's go back for a second and talk about the term error, because error, students often think about means mistake. But in science, when we're talking about lab work, error does not mean mistake, okay? We always have error in lab. We always have some systematic error because we do not have perfect equipment and we don't have perfect eyesight. So we have to make some human observation about where that water line, where that meniscus hits where it falls relative to those lines. We also have random error, and random error is due to laboratory techniques. So we might be measuring something, in fact, in the wrong way. So random error is something like, let's say I am measuring the mass of a substance, and I put the weighing dish on the electronic scale, and then I add the substance to the weighing dish, and I report that mass as the mass of the substance. I would have random error because I could do it 100 times and do it 100 times wrong and get that same error every time, because in every case I would have forgotten to subtract out the mass of the weighing dish. Okay, so we talk about accuracy and precision. Accuracy is how close to the true value I am. So if I am measuring the density of something, let's say I'm measuring the density of aluminum in the lab, and based on my measurements, I calculate a density of, let's say, 1.9 grams per milliliter, and the accepted value, the value I can look up online or I can look up in my textbook, is 2.7 grams per milliliter, then my results are not accurate. Okay? Precision is how close measurements come to each other. Okay? And it's also related to the measuring device. So a graduated cylinder is more precise than a beaker, because multiple people can look at that graduated cylinder and get that number more precisely, more the same each time than they can on the beaker, where there's going to be more variation. Okay, so precision, if I have 3 measurements and they are all close to each other, 3 trials, then my results are precise. Now I can be precise without being accurate. Okay, so let's take a look back. Oops. Okay, so let's take a look. I already put the answers up, but if I look at trial, if I look at, let's start with A, and on A, all of these values, the dotted line here represents the accepted value, and because all my values are close to the accepted value, all my data points, then I am accurate. And because all of these values are close to each other, I'm also precise, which is why A is both accurate and precise. If I look at B, my results are not accurate. Here's the accepted value. Here's my lab values. They are not close to the accepted values. So therefore, I am not accurate. But they are all close to each other. So in this case, I'm precise but not accurate. So this is the kind of thing I forgot to subtract my weighing dish. So I keep getting the same wrong answer. And each time it's pretty close to each other. If I look at C, here I have each result, each trial is not very close to the accepted value. But if you see, I have equal amount above and below the value, and if I average those, the average is going to actually show to be close to the accepted value. So we might average, report the average, say our results are accurate, even though each value is not all that close. And because my data is so scattered, it is clearly not precise. So I would end up, most people would end up calling this accurate and not precise. If I look at D, here's the accepted value. I am not accurate, and I'm always in the same direction. I'm always high versus the accepted value, and my results are not close to each other. Okay, so it's important to know that in the lab we want to be both accurate and precise. All right, so let's talk about what is measurement and what's uncertainty. So measurement is the data. It is never the calculated value. So when we put together a data table, we only want the facts of the experiment. The facts are those things that we measure or those things that we observe with our senses. They are never calculated values. Okay? And the uncertainty is the estimated value. Okay? So if I have a beaker, right, and my water line falls right here, I know that that volume is between 40 and 50 milliliters, okay? But I have to estimate how far between 40 and 50? Is that 45? Is that 47? So the way I estimate and you estimate are going to be a little bit different. So there's some uncertainty in that value. And the last digit is always estimated, and it's always estimated between the two smallest grid lines that I can see. Okay? So I can see it's between 40 and 50, and I have to report one more value. So I might report that this is 47, okay? Someone else might report it's 46, someone might report it's 48. So that's why we call it estimated. There's a little bit of uncertainty there, okay? But I still report it. I don't report it as 40, don't report it as 50. I report it as 47. I estimate the last digit. If I look at the graduated cylinder, it's between 20.3 and 20.4, and therefore I have to estimate one more place, okay? All right. So why does it matter? Does 2.00 and 2 mean the same thing? In the 2.00 value, if I report that, that means that I know for certain it's 2.0, and I have an estimated value for the last digit. If I were to report something as 2, that means that I don't even have certainty on this digit. That would mean that I have some device where this is 0 and this is 10, and I can only estimate in between. Okay? All right, so the measurement you report tells the reader, the scientist reading your report, how precise your glassware was. Okay. All right, so that leads us to this whole concept of significant digits or significant figures. Okay? Okay, so significant digits are those measured to estimated numbers. Okay? So this is whether I report 2.00 or 2, okay? The fact that I wrote 2.00 tells me I know that answer more precisely based on my measuring equipment than if I were to report 2. It tells the scientist reading your report how precisely you know that value. Okay, so let's talk about the rules for what's significant. So if I have a value, let's say 2.0125, all non-zeros are always significant. So the 2, the 1, the 2, the 5, always significant. The issue with significant figures or significant digits is always whether or not the zeros are significant. So if I have placeholder zeros, they are not significant. So if I have the number 0.00125, these numbers, these two zeros, just are, the only reason they are there is to hold place, is to indicate the magnitude. I can't write this as 0.125, okay? They are there as placeholders, okay? Also, if I have the number 200, I may know for certain this number in this number and not this number, or even not this number. Ending zeros, if there's no decimal point, are not significant. What I don't know is, do I know there's exactly 200 things, or am I estimating 200? Okay? So if you say, how many students are taking, let's say, a blended course this year, you might say there's 200. You don't really know whether that's, you know exactly there's 200 or you're estimating. It could be 230, it could be 190, but when you say 200, there's some uncertainty about whether or not, how precisely you know that number. Okay, so leading zeros are not significant, and ending zeros are not significant if there is no decimal. Okay? So if we look at 0.001 kilograms, they're leading zeros, so they are not significant. Here I have no decimal place, 2,000 kilograms. They are ending zeros, so they are not significant. Okay? If I look at this number, the leading zeros are not significant. Now the ending zero is significant, because you got to ask yourself, why was this zero written? If it's not significant, I wouldn't write it. Okay? 0.0001. If I wrote that, that's kilograms, right? That's different than writing this. It means I have more certainty with this number than I do with this number. So the only reason to report it is because I know it, because it's part of my estimation, my estimated value. Okay? So now, if I look at these numbers, they are there just to hold place. I have to have them in there because if I wrote it as 0.10, that's a very different value than 0.0010. Okay. So what about exact numbers? Okay. So if I go on to eSchools and I am able to count as an administrator how many students are taking blended classes this year, I can say there are 201, or maybe there is exactly 200. If I know that's a counting number, if that's based on an actual counting number, then all of these numbers are significant. Okay? It's not a measured value, it's a counted value. So, for example, 465 books, or 23 students, or 10 dozen. If I have 10 of something, it's probably something I know exactly, right? So both digits are significant. All right, so let's take a look at some practice. For each of the following quantities, we want to underline the zeros that are significant and to determine the number of significant figures in each quantity. Okay. So for D and F, we want to express in exponential notation first. So let's take a look at A, B, and C together, and then you're going to try D, E, and F. Okay? So for A, the leading zeros are not significant, only the trailing zeros, because there's a decimal there. Okay? The leading zero here is just there to make sure I can see my decimal point. It's just good form if you have a decimal to put a zero in front. Okay? But the zero here after the 1 is significant. The zero here in this number is sandwiched. Do you need it there? It's significant. Okay. All right, so if I look at D, E, and F, let's not express them in scientific notation. These are leading. These would not be significant. Okay? Now, these are trailing, and if I put a decimal, there's a decimal point there, that means that I know those values. So those are significant. Okay? These are significant. Nothing here is significant. The only thing I have is this, so there are 4 sig figs. Because these zeros are significant, I have 1, 2, 3, 4, 5 significant figures. And here, the leading zeros, it's a decimal, are not significant. But the trailing decimal, the only reason to report it is if it's significant. So I'm going to have 4 here. All right. So let's talk about scientific notation. First, what is it, and then when is it used? So, scientific notation is using exponents or powers of 10, usually for very large numbers or very small numbers. So if you asked me how many atoms there are in the head of a common pin, I would tell you that there is about 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Can't even fit them all, right? It's a 1 with 12 zeros. Or I can say 1 times 10 to the 12th. It's not realistic to write all these zeros, and we are always, in chemistry, talking about very large numbers when we're talking about how many atoms there are somewhere. We are also often talking about very small numbers. So if you ask me what the mass of, let's say, one aluminum atom is, I would tell you it is 1.6 times 10 to the minus 23 grams. If I had to write that number out, it is going to be 1.6 with 23 zeros before it. Now, I don't think you're going to be wanting to write all those numbers. So we use it for very large and very small numbers. All right. So when we're converting between scientific notation and standard form, the rule is there will always be one digit in front of the decimal place, okay? And then I'm going to move my decimal place wherever it starts, and here it's starting right at the very end, right? The decimal point starts, whoops, after that last zero. It's there, right? Pretend it's a decimal. And I count how many times I have to move my decimal place, okay? And when we write in scientific notation, we only include significant digits. Now, this one should be 3.69 times 10. 1, 2, 3, 4, 5, 10 to the 5. I count how many places I have to move the decimal. So it's 1, 2, 3, 4, 5. So this should be a 5. If I want to convert this, then I am going to move my decimal place 1, 2, 3, 4, 5, 6, 7, 8. Okay, you get the idea? My decimal point is here. This is a small number, so it's gonna, I like to think a small number is gonna have a negative exponent. So I'm gonna count how many places I move the decimal. 1, 2, 3, 4, 5, 6. I'm moving it 6 places, so I'm gonna report it as all of the significant digits. Okay, and then the exponent of negative 6. Okay, here I have 5.00. It's 10 to the minus 4, so I have to move the decimal the other way. It's going to be a decimal, and that's what I get. Okay. Now this 0 is significant. The 5.0, the 0.0 is significant, so I need to include that when I write my longhand. All right, when I use a calculator with scientific notation, I need to use the EE function, and we'll show you in class if we want to make sure that you're getting the right number when you punch, because punching is half of the problem, which is part of why you need to have your own calculator so you get comfortable with what the buttons are on your calculator and how to do this, okay? We don't ever want to use the times 10. That'll end up giving us the wrong answer in some of these notations, okay? We really don't want to use the caret either. Okay, for significant figures using calculation, we need to keep, why is it important to keep track of the significant digits? And that's because the calculation should reflect the precision of the measurements. You can't have a calculated value that's more precise, that is more precise than the measurements, okay? So that's the basic rule. All right, so if we're adding and subtracting and we want to round to the smallest place value, okay? So in this case, what that means is I have 1 decimal point here, I have 4 decimal points here, so I want to go with the one that's the least, so I'm going to go with 1 decimal place. Okay? Here I have 1 decimal place, 2 decimal places. I'm going to round my answer to the smaller, so I'm going to round my answer to 1 decimal place. So first I do the whole calculation, and then I round to the smallest. Okay? So in both cases, I want 1 decimal place here. In multiplication and division, which is much more common in what we do in chemistry, we want to round to the lowest number of significant figures. Okay? So if I multiply 6.09 times 9.2 times 0.3418, let's see. Here we have 3 sig figs. Here we have 2 sig figs. Here we have 4 sig figs. My answer cannot be precise and my least precise measurement. In that case, it's the 2. So when I punch this into my calculator, I get 19.15, but I've got to round that to just 2 sig figs. And when I do that, I have to report to 19. Now I'm also multiplying centimeters times centimeters times centimeters, and that's going to give me centimeters cubed. Okay. So the rule on rounding is I want to round 5 and up to the next number. Okay. So if I were reporting 3 sig figs here, I'd report this as 19.2 because this 5 will round up. Alright, so one of the important rules in chemistry or in doing these calculations is we never round until our calculations are complete. So we take our calculations with as many digits as our calculator will hold as far as we can, and we don't round until the very end. So if I can punch all this into my calculator in one step, I am better off. Okay? So here I have 4 sig figs, 3 sig figs, 5 sig figs, 2 sig figs. My answer, I want 2. Don't make the mistake of multiplying this times this and getting 2 sig figs, rounding it, and then take this and round it, because I will not end up with the same answer. Okay? Alright, so we're going to stop right there.